Our next paper is Evaluation of Marginal Likelihoods via the Density of States, and will be presented by Michael Habeck.
Welcome. So this will be about calculating high-dimensional integrals, things that you need to do if you do Bayesian inference. So just to start very gently, let me introduce some notation basically. So this is what you do in Bayesian inference. You're trying to learn a model M parameterized by some parameters theta from some observations D. In order to do this, you need to decide on two probabilities, the likelihoods or probability of your observations given the model, and the prior over the model parameters. So this is what you assume and what's known, and then the left-hand side gives you the inference, the posterior, which you can use to infer the model, to sample model parameters, for example, and the marginal likelihood or evidence. And these are the symbols that I will use throughout the talk. So we are basically interested in calculating this quantity, which is just a number. Okay? So why is this useful? If you compare two models, let's call them M1, M2, and you compare them via base factors, you need to evaluate the marginal likelihood of each model and then compute the base factors. So this is the task that we want to tackle. We want to solve this high-dimensional integral or sum. And if you have some background in physics, this quantity is analogous to partition function, or you could also view it as the prior expectation of the likelihood. Okay. So how can we do this? So there are, of course, methods like the Laplace approximation that one could use, but these are limited inherently if your posterior is multimodal, for example, or if it's skewed and the Gaussian doesn't really fit well. So what we do is use Markov chain Monte Carlo sampling, and the basic idea is to introduce a whole class of posterior distributions that span all the distributions between the prior and the full posterior, and you do this by introducing a temperature-like parameter, which I call beta, and by letting beta from 0 to 1, you can basically morph from the prior to the posterior. And the normalization constant here is then a function of this reciprocal temperature. You can use it to evaluate the evidence. So what you do is you sample from a whole set of different tempered posteriors. You might allow for exchanges if you do parallel tempering. And then we want to use these samples in order to evaluate the evidence. So what people do in thermodynamic integration, which I will explain on the next slide, is basically estimating this function. And we will explore an alternative to this. So thermodynamic integration uses the following identities. If you take the derivative of this normalization constant with respect to this temperature-like parameter, you observe that it's equal to the expected log likelihood in the anneal posterior ensemble. So now you can revert this operation by calculating an integral over these expectations of log likelihoods at different temperatures and recover the log evidence. And this is basically what people do when applying thermodynamic integration. Of course, this function is only known on the support points, on the temperatures that you chose. But if you have many enough temperatures, this is a good approximation. So this is basically the trapezoidal rule. So here I will use a different approach. I won't try to estimate this function basically or the normalization constant. I will focus on what people in physics call the density of states. So this is defined like that. It's a one-dimensional density over energy or negative log likelihood. So I will just use energy for convenience. So this is basically just summing all the prior mass of states that map to the same negative log likelihood value. So if you knew this function, evaluation of the marginal likelihood would be simple. So you see this if you look at the normalization constant. So this is the definition. You write this in a more complicated way. This is just, so this thing in brackets is just a way of expressing this. But as an integral, you exchange the integration and then you end up with a one-dimensional integral, which involves the density of states, which tells you that the normalization constant and the density of states are related by a Laplace transform. In thermodynamic integration, you're basically looking at this object or a derivative of that object, whereas here I'm trying to estimate this object. So the basic algorithm is to use these MCMC samples, estimate the density of states, and then evaluate the evidence as a one-dimensional integral over the density of states. So how can we do this? So I will use maximum likelihood, so I will commit a sin, but this is, for the time being, that's well, what we can do, and it leads to a very simple algorithm. So what I consider here is an even more general setting where I have a family of bridging distributions, so sort of modifications of the posterior. I have the prior, and then something that I call an ensemble or a replica, which just depends on the parameters via the log likelihood. So so a special case of this is, of course, the posterior that we just talked about, but you can also think of more general ensembles like the one that Skilling is using in nested sampling, where this is not the Boltzmann factor as here, but a likelihood contour, basically. And also for these types of ensembles, you can recover the density of states. So in that respect, the method is already more general than thermodynamic integration, which I guess requires, this is just working for this particular family. So how can we do this? We do maximum likelihood, so we need the likelihood of observing a particular log likelihood value, assuming that we know the density of states. So this is this probability, basically, and it depends on the density of states, so through the normalization constant and also the density of states shows up here. So this, the ensemble basically drops out because it doesn't depend on the density of states. So if you do maximum likelihood, you minimize the negative log likelihood of the density of states. So you get these two contributions. So this is the one from here, and this is the one from here, and this is really now a functional, since the density of states is a function. You want to this is an infinite dimensional object that you want to recover. So let me reparameterize this by using this function u, which is the log density of states. And I just do this for convenience. So if you plug this in, the log kills this exponent, and this is just a more fancy way of writing a sum over all these u evaluated at EI. And this involves the energy histogram, and the second term is just a sum of logs of this normalization constant. And what you appreciate easily is that this is convex, so this is just linear in U, and this is basically a continuous version of log sum x, which is a convex function. So this is nice because it tells us there's only one optimum. We can try to find that optimum by calculating the functional derivative, but this gives us an implicit equation which we can't solve explicitly for u. So it's not possible. Instead, we use a variational approach, so we iteratively construct an upper bound which we update instead of the real log likelihood functional. So this is this upper bounding functional. It touches L if u equals v, and these are the iterations to learn the density of states. So you start with a flat density of states, you calculate this upper bounding functional, and then you minimize it with respect to the first argument. And you can do this analytically. So this is the expression basically that you obtain. So this is still in function space, so it's not convenient to work in function space. But if you now use this expression, calculate the normalization constant, you obtain an iterative equation for the normalization constants. Okay, so you obtain this thing, and this is nice because it's all finite dimensional. There are no functions involved any longer. And instead of using this, we update, basically, we go into log space because it's more convenient. So these are the final iterations that we use. And you can express also this loss function that I introduced before in terms of these free energies up to one constant. And you can use this in order to monitor the convergence of your updates. It's also nice. So this is the final estimate then of the density of states. So it involves this energy histogram, which is then reweighted by these terms here, and the free energy shows up here and basically determines how much the individual ensembles contribute to the density of state. If you take this estimate, plug it into the definition of the evidence, you can carry out all the integrals analytically because this is just the sum of delta functions, and you obtain basically this sum here, which involves your estimate of the density of states for that particular energy level that you sampled. So this is the method. Now there's a simple application just to get started. So here I took a Gaussian likelihood, and then I restricted the Gaussian to a unit sphere in order to have compact support and a normalizable prior. So you can do all the calculations analytically. This is just comparing the density of states that I estimate. So this is this thin white line here, and this black band here is the analytical result that one can calculate, and you see that they coincide quite nicely. So this is the inset shows the error that you do, and you realize that at low energies, so in the region where it's really important to be correct, you're doing a quite good job. This is monitoring the convergence. So this is this loss function expressed in terms of the free energies, and as it should, it converges monotonically, decays monotonically. This is a comparison of thermodynamic integration and this density of states based estimation of the log evidence. So what I did is run 1,000 of these annealed sampling runs and evaluated the density of states and accumulated histograms. So the gray histogram are the estimates obtained with thermodynamic integration, and the black line is the result with the DOS, and both coincide nicely, and they scatter about the true value, which is indicated with a red line here. And this here is showing that both estimates are quite correlated. So this is for this was for the case where I used 10 temperatures, and of course in MCMC you would like to save resources. So one way of doing this is to use fewer temperatures. So this is what I look at here. So this is again at 10 temperatures. So this situation basically where both methods do equally well. Okay. And if I decrease the number of temperatures, thermodynamic integration, which I show here as orange dots, starts to have problems, because of course then this finite approximation of this trapezoidal rule starts to have a problem, because you have only few support points, whereas the density of states still works nicely. And this is the same effect if you don't go to beta equals 0, but to finite beta greater than 0, which is something you want to do because you don't want to sample from the prior. And again, the Dawes method is more robust. So these are just other examples. I guess I will basically skip that slide. It's just showing you that, again, both methods work very nicely for not so tough likelihoods, but if the minima become really deep, like for these two cases, the Dawes estimate is more accurate. So for the remaining for the remainder of the talk, I will talk about the application that I'm mostly interested in. So this is to infer protein structures from experimental data coming, for example, from NMR spectroscopy, and we have developed a Bayesian approach to do this. So here, your parameters are the rotations about these covalent bonds that parameterize your protein polymer, and there are typically several hundreds or several thousands of these angles, and they're of course highly correlated. So this is from the sampling point of view, I guess, a challenging problem. So what we could show is, if you do this Bayesian sampling approach, which I show here on the right-hand side, you're doing a much better job, especially if the data are sparse. So that's where Bayesian methods typically are performing much better. So in the traditional approach, which is based on optimization, the structures that you sample are basically have nothing to do with a real structure, which I show here as an orange ribbon. But so coming back to that model comparison, so this is the parallel tempering scheme that I use. So I have two temperature-like parameters. So one for the likelihood. So this is, I just call this lambda, but so it's equal to beta. And this is a second parameter which allows me to deform the prior. So the prior is a Boltzmann distribution. So it's this thing. Okay, and this is a physical energy. So it models the interactions of the atoms in the protein, the pairwise interactions. And I use a Thales ensemble, which is identical to this thing if Q equals 1. If you increase Q, then this allows you to flatten out the prior. So the total parallel tempering chain is made up of two subchains. So in the first part, I decrease Q for a fixed small lambda. And then in the second part, so I basically turn on the prior, and then in the second part, I also turn on switch on the data. And you can use this second chain here in order to do thermodynamic integration. But what's nice about this Dawes method is that you can use all the samples. So you can generalize the method to two-dimensional or higher dimensional densities of states, and you can use all samples also from other temperatures. So from this chain here, you can also think of of a chain where both parameters are changed at the same time, which is the most optimal thing to do. So this is just comparing two of these functions here. So one is the first one, which is normally used in the NMR structure calculation, just models atoms as soft balls, which don't want to interpenetrate too much. And the second potential is more realistic. It has also a small attractive van der Waals term. And this is just comparing these two energy functions, and both methods agree that this physically more realistic energy function is doing a better job. Okay, and if you compare this, if you look at the accuracy of the estimated structures, also the structures are of higher quality. So this is what I said before. The DOS method allows you also to use a more efficient replica scheme or temperature scheme. So let me finish by wrapping up. So I introduced this DOS-based evidence estimation, which is a simple alternative to thermodynamic integration. It just involves these iterative updates of the free energies or normalization constants. It's more robust, it's more flexible than thermodynamic integration. This DOS itself is, I think, a useful quantity in itself, so you can use it also to resample states at different temperatures. You can also use it to calculate marginal distributions. And in the future, I'd like to look into a truly Bayesian version of this thing. This is, so what I told you is still maximum likelihood only. And I didn't have time to talk about this, so there's a close connection to nested sampling, and would be nice to somehow combine the two methods. Okay, that's it. Thanks for your attention.
Very interesting. What was the distribution you placed on beta for the experimental runs that you used, and how did that impact the difference between PI and DOS?
Yeah, so in the paper there's also a graph showing that the temperature schedule is more critical. To have a good temperature schedule is more critical for thermodynamic integration. So for this Gaussian sphere, for example, I just used a quadratic scheme, I guess, or something like that. But in general, of course, this is something you don't know. And
could you get an optimal form for that distribution over beta for the DOS? Because you can get it for thermodynamic integration.
Yeah, so you can use the DOS to calculate the expected exchange rate. And you could use this to optimize your temperature schedule. But of course, then this is another iteration and an outer loop. But what would be nice is to basically do MCMC and also update the DOS somehow at the same time as it's done in nested sampling, something like that. Yep.
So would the Bayesian scheme help with that? Is the idea there that you actually perhaps select temperatures to improve the estimate, or what else would the Bayesian scheme do?
Yeah, I mean this DOS looks a bit odd because it's just a sum of delta functions, which seems like it's completely overfitting, and that's. And of course, what I'm interested in is also to look at multidimensional DOS functions. So really having marginal distributions over other parameters, and at some point, I guess you need some kind of smoothness also. And this is what I would like to include here. I guess just for the purpose of evaluating the evidence, that's fine. Yeah.
questions?